Okay, welcome everyone to the Topos Institute Colloquium. Today we're very happy to have Arthur Parzygnat talking to us about a generalization of inversion using Bayes' rule. So go ahead, Arthur.
Thank you very much, David. And thank you also for the invitation. It's very exciting to talk about these ideas, primarily because it's a very interesting intersection between quantum mechanics and also category theory and categorical probability theory. And, and so I'll try to make my talk as introductory as possible. So feel free to ask me questions at any time, especially clarifying questions. If they're super technical questions, I may, in the interest of time, push those to the back of the talk so that we can have more time for discussions. So this talk is based on two papers primarily. The first one is on the left. It's a paper that I wrote together with Francesco Buscemi, who's a quantum information theorist at Nagoya University. And also a paper on the right, which was a bit more recent, which is more along the lines of trying to get down to the categorical axioms and making them more formal in a way that reproduces the results that were obtained on the left from a more quantum mechanical perspective. So before I get into the nitty-gritty of the category theory, I just want to talk a little bit briefly about Bayes' rule, Bayes' theorem, and Bayesian inference in the classical setting. So first of all, it's used ubiquitously. And just to give you a rough idea, you could use it to, for instance, determine the disease of a patient based on the symptoms that they have or the tests that they take and prior knowledge on the prevalence of those given diseases. You can use it to estimate the fairness of a die based on a finite number of outcomes and your prior guess as to whether the person who is throwing the die is trying to deceive you or not. You could use it to determine future weather patterns based on the previous ones. You could use it also in the applications of quantum mechanics to determine, for example, the state of a quantum system based on measurements and their outcomes. You could use it for error correction schemes. You could use it to bet on horse races or other probabilistic games. You could use it for artificial intelligence and machine learning. And the list goes on. And part of the motivation here is to try to understand if we can make sense of a quantum-based theorem, what that would look like, what is the mathematics behind such a theorem, and can we use it for quantum decision processes or inference, or what else can it be useful for? Is it as ubiquitous, for example, as ordinary Bayes' rule is in classical probability theory and statistics? So that was just a motivation. That was my first motivation slide. I have another motivation slide, which is coming from a relatively recent categorical rethinking of probability theory. So this is slightly different from the algebraic rethinking of probability theory that I think dates back to the 60s, perhaps, and the 70s, that eventually led to non-commutative probability theory and free probability theory. This is a different line of thought where, as was observed by Brendan Fong, Kenta Cho, Bart Jacobs, and later Fritz, that you can formalize the idea of a Bayesian inverse or Bayes' rule in terms of string diagrams. And I will explain these in more detail later on in the talk. This slide is just to give you a rough motivation of where I'm coming from. And the idea is that if you're given a state, which I'm representing as a morphism in some category from a very special object, I, it's going to be the monoidal unit, into another space X, another set X or an object X. And I interpret that as a state. And there's also going to be a morphism from that object X to another object Y. And given those two pieces of data, I can define a Bayesian inverse as a map, a morphism in the opposite direction that satisfies a certain commutative diagram, which I can encode as an equality of two string diagrams. And this idea works quite well using Markov categories or classical categorical probability theory. But unfortunately, the copy map, this map that appears in these string diagrams, is not a valid operation or physical process in quantum theory. And I'll say what those are later on in the talk. And even if I ignored the fact that such a map, I can create such a map, but it's not a physical process. But even if I ignore the fact that it's not a physical process, I can still try to formulate the same definition regardless. I can say, okay, well, if you give me a state, in this case, a quantum state is viewed as a linear map from complex numbers to some matrix algebra, A, for example, and I have an evolution map from A to another algebra, B, then a Bayesian inverse would be a morphism in the opposite direction that satisfies this equality of two string diagrams. I can still make sense of this definition, but it's a little questionable about its meaning. And not only that, but it turns out that this morphism satisfying this string diagram equality that is used very often in the setting of categorical probability theory turns out to rarely exist. Almost never does such a map exist, only under special circumstances. And here's just some sample of papers that go into the discussion for when these kinds of Bayesian inverses exist. And the point of my talk will be to, in some sense, fix this problem, find a method, find a categorical way that obtains a notion of a Bayesian inverse that is weaker in some sense than this idea. So let me, actually, maybe I should pause if there are any questions at this stage just to get the rough idea of where I'm going with this talk. Okay, so let me start off by giving a definition of what a Markov category is so that we can actually make sense of those diagrams that I drew a moment ago. So a Markov category is a symmetric monoidal category where the unit is a terminal object and where each object, let's call it X, comes equipped with a morphism from X to the tensor product of X with itself. I'm going to call this morphism a copy map. And the reason I'm going to call it a copy map comes from the fact that it satisfies a bunch of compatibility conditions. One of these compatibility conditions is sometimes called broadcasting. And I'll say what those little grounding operations are in a moment. Another axiom that you want the copy map to satisfy is called, well, technically it's called co-associativity. And another one involves a compatibility with the tensor product, the monoidal structure on your category. So what are some of these morphisms that appear in these pictures? The grounding operation, which is drawn as like a circuit from grounding, is a morphism from X to the terminal object. And because it's terminal, it's guaranteed to be unique. There is also a morphism that appears in the diagram on the right, which is called the braiding of the category because it takes you from X tensor Y to Y tensor X. So using these ideas of a Markov category, in fact, you don't even need all of this to describe what I'm saying, but this is the setting that we're in. We can make sense of what a state is in a Markov category. And if you're given an object X, a state on X is a morphism from this terminal object, from this monoidal unit, into your object X. Now, if this is your first time thinking of states like this, for example, you can take the category sets. And if you think of a state as an element in your set X, then the terminal object in the category of sets with the usual Cartesian product as the monoidal structure, then then this terminal object is just a single element set. So in this case, a morphism from the single element set to X picks out an element. So that's part of the motivation for why I'm thinking of states in this way, and we'll see other examples later that give a more robust notion of state. And I'm going to draw those in terms of string diagrams on the right. In this case, morphisms in a Markov category, I will think of them as channels. And the reason is because in the examples that I'll give, they generally correspond to noisy classical channels or stochastic matrices or quantum channels, or which are viewed as quantum extensions or generalizations of stochastic matrices. So I want to talk about the first example of a Markov category. And this one is the one of discrete probabilities and conditional probabilities. In this category, an object is a finite set. So here's an example of a finite set. I've drawn a set with 4 elements. I've labeled and colored them. And the reason why I colored them will be apparent in a moment. That's because what is a morphism? A morphism from an object X to an object Y is not a function, but rather it associates to each element a probability distribution on the target space, on the target set. So now you can see maybe a little bit better about why I colored these elements in X. Let's say the set X is the set of these 4 elements, and the set Y is the set of these 3 elements. So I'm not taking, Y is not a set of 12 elements, it's just a set of 3 elements. I've just repeated the picture a bunch of times. But to each element in my input, like take the element that I've labeled 1, I'm associating a probability distribution on the set of 3 elements. And I'm visualizing that probability distribution as a water droplet, or just a droplet. This idea came from Gromov. And the size of the water droplet dictates the relative probability of getting that element out. And so if I look at the collection of all of these numbers, then the collection of all of these numbers is sort of like a matrix. In this case, it would be a 3x4 matrix. And the entries of these matrices would give me the conditional probabilities of getting Y, given that I started in X. I can also think about states in this setting. Here, I corresponds to a single element set. And so a morphism associates to its unique element a probability distribution on X. So rather than thinking about the category of sets, right, where we thought of a state as an element in my set X, I'm thinking of a state now as associating a single to the unique element in my terminal object. I'm associating a probability distribution on the set X. So there are many, many more states on X than they were in the case of the category of sets. And just for simplicity in this talk, I will assume that all of my states are nowhere vanishing. I can give a talk also about what happens when you allow probabilities to vanish, but it gets a little technical, and I think for presentation purposes, it's a little bit easier to avoid the discussion of what happens when you divide by 0. All of these things can be handled, but I don't want to refer to those details at present. So let's keep going with trying to explain how Finstock is a Markov category. We have to define the tensor product, the monoidal structure, and that's just given by the Cartesian product of finite sets. The tensor product, the monoidal product on morphisms, turns out to just be the multiplication of the numbers, the actual conditional probabilities. So that x actually you see on the right is multiplication of real numbers. And the composition rule is given by just matrix multiplication. If I have a stochastic map from a set of 4 elements to a set of 3 elements, and then from 3 elements, I don't know, 7 elements, then I'm going to sum over all the intermediate 3 points to get a matrix that's 7 by 4. And the idea is that stochastic maps push forward probability distributions. So if you plug in a probability distribution and you apply the map F, then you're going to get an output probability distribution on your target. This is sometimes called belief propagation in the literature. So this summarizes one example of a Markov category. And I should say that in this case, the copy map is the function from x to the Cartesian product of x cross itself that sends an element x to the element x comma x with probability 1 and 0 probability elsewhere. So it's the usual diagonal map from the category of sets.
Sorry, Arthur.
Yes.
Does that go against your nowhere vanishing?
Yeah, so I'm allowing my states, I'm allowing my morphisms to have vanishing probability as long as it's not the states. And you'll see why in a moment.
Got it, thanks.
The point is, everything I'm saying will make sense if I allow zero probability. It's just I have to be more careful about what I say. Yeah.
Gotcha.
So actually on this point, let's actually now talk about this primary category of interest, which is actually not the category Finstock, but the category of its states and state-preserving morphisms. So this is in categorical lingo called the co-slice category, but I'll explain what it is right now. So here the objects are pairs this time. The first element in this pair is a finite set X. And the second element in this pair is a state on X. And these are the things that I require to have non-vanishing probabilities. A morphism from one such pair to another is a stochastic map from X to Y that sends the probability P to the probability Q by that matrix multiplication formula I showed on the previous slide. We call these morphisms state preserving. So in case I use that terminology, that's what I mean. And actually, this construction makes sense for any Markov category. So in fact, this construction will make sense for a larger class of categories besides just Markov categories. But those are the ones that I want to focus on for the moment. There's an interpretation of this category in our example of Finstock and its associated category of states. The idea here is that I think of the first probability distribution P as what's called a prior. I set up a probability distribution on my finite set X, and let's say this is the probability distribution that I've perhaps gathered based on some knowledge of what the probability of any element X could be. Like, for example, I've looked at the last year's record of the weather patterns in my area, and I found out that, I don't know, 100 days out of 365 it rained. Maybe I'm in Seattle. And I tabulate all of those probability distributions based on the evidence that I have. So this is called the prior. And the map F, the stochastic matrix F, pushes forward that probability distribution. And this collection of conditional probabilities, the probability of Y happening given my input X, is sometimes called the likelihood. And when I sum over all of the intermediaries from the space X, I get my prediction. based on the probability of given weather patterns, what is the probability that somebody will take an umbrella to work or something like that? It's also sometimes called the marginal likelihood. So let me illustrate this in a slightly more concrete example, just so we see things in a moment. So I'll do so after I just finalize describing what this category, what the structure of this category looks like. So the composition rule is the same thing that we had before. It's the underlying composition of the morphisms between the original sets X and Y and Z. And the tensor product is also the same. So that's the structure of this category. It inherits a lot of the structure from the previous one. So when we have such a structure, we can define a Bayesian inverse. So a Bayesian inverse is associated to every morphism in this category of states from X to Y. And it's a morphism in the opposite direction that satisfies this diagram. Rather than explaining all the details behind how you read these diagrams, I think it's helpful in this example to see what it means in the context of finite probability spaces. So in this setting, the left-hand side of this diagram turns out to be what's called the joint probability of measuring X and measuring Y following X and the evolution from X to Y. That's the probability on the left. If I read the diagram on the right, it's corresponding to some potentially new joint probability distribution that says, I'm going to measure the outcome Y, and I could infer what the probability of X was given that I saw Y. That's this F dagger. That also defines a joint probability distribution. And Bayes' rule says that these two joint probability distributions are equal. Because they're equal, you can solve for one of these, you can solve for this Bayesian inverse. And that's sometimes called the posterior in the literature. And that also defines for you a stochastic map. So how do I interpret this? The Bayesian inverse is used for inference. Namely, if you are given evidence Y, then this Bayesian inverse gives the updated probability for X, given that you've also observed Y. So here's a super concrete example. Let's just say that our spaces X and Y are both two-element sets, but we interpret them differently. The set X is whether a given individual has a disease or does not have a specific disease. And let's say Y is the set where that person goes to a doctor and they take a test, and the outcome of that test is positive or negative. So let's say that the disease has a certain probability of being prevalent within a population, and let's say that 1% of those people have that disease, and therefore 99% don't. You can also assume also that you know whether the test gives you what are called false positives or false negatives. And let's say you know that if you have an individual who has the disease, takes a test and receives a positive outcome, let's say it's 90% chance that they got a positive outcome. And if they don't have the disease and they take a test and they get a negative test result, let's say that's 95%. So given these statistics, the doctor has to, or any individual can figure this out on their own too, using Bayes' rule, says if that patient goes to the doctor, takes a test, and then they have a positive result as an outcome, you can ask the question, what is the probability, given this information, that they actually have the disease or not? And if you work out the math, sorry, that bar should be a dagger. If you work out the math, it says that roughly you have a 15% chance of actually having the disease, given that you've gotten a positive test result once. Of course, you would, in this case, the test results are not very informative, so you would probably take another test or two just to confirm for yourself whether or not you have that disease. So this is generally how Bayes' rule is used, and this is the simplest example I could think of where you have two non-trivial sets, so of size 2 and 2. But you could imagine that this is, you can scale this up and use this more broadly. So that was the definition in terms of string diagrams. And now I want to emphasize another perspective on Bayesian inversion. So here we have the category of states, and we're taking our morphism from xp to yq. So we take this stochastic state preserving map, and then we construct a new map in the opposite direction. And something like that should already feel a little bit familiar. Imagine you have a group, right? Imagine you have a group and you have a symmetry, and you maybe know what that symmetry looks like, maybe as a matrix, and you want to invert that group element to get a map going backwards. This is kind of the idea that I want to really emphasize here. And it turns out that this assignment that takes an object, xp, that takes a finite set with a state and doesn't do anything to it, so it just leaves it alone, but it takes a morphism and then it reverses the order. This map that sends f to its Bayesian inverse defines an identity on objects, inverting, involutive, monoidal functor. So it's a really big mouthful, and there are a lot of properties here. But I think maybe many of you can appreciate, first of all, that it's a functor. Second of all, it's monoidal. It's identity on objects. Maybe some of you might know what involutive means, and maybe fewer know what inverting means. So I'll explain all of these in a moment. But first, why did I call it R? Really just R because R maybe stands for retrodiction or reversal. Retrodiction, by the way, if that vocabulary is unfamiliar, is the opposite of prediction, right? In prediction, you have a state, and just as I explained before, you have an input state and you have a process that evolves that state. You can predict what the probabilities are in the future. Retrodiction is the opposite, where you see something that happens in the future and you try to retrodict what could have been responsible for that event in the past. So let's go through each of these one at a time. So identity on objects, that's what I said it means just a moment ago. It fixes each object. So really the content of this functor is really what's happening on the morphisms, not so much on the objects. It's inverting. This means, interestingly, that if I take a morphism, which means a state-preserving map, that happens to be an isomorphism in the categorical sense, right? Which means that there exists another state-preserving map in the opposite direction, such that when I compose the two, I get the identity morphism on that object in both directions. So this functor that I was talking about, Bayesian inversion, satisfies the possibly, surprising property that if my morphism happens to be invertible, I get the inverse. So that little comment that I meant earlier about the fact that I'm already restricting myself, this map R, to give me an actual stochastic matrix is actually what guarantees that it's that the inverse is going to be an actual potentially a physical process. Namely, it associates probabilities. Now, this is a general question for the audience. I'll probably ask for opinions once I go through describing all of these items. But I would like to know if this has a better name in the literature. So I'll explain what I mean towards the end of this slide. So it's also involutive. Involutive means that if I apply this functor twice, so if I take the Bayesian inverse and then I compute the Bayesian inverse of the Bayesian inverse, I get back what I started with. It's monoidal, so it respects the tensor products, and it's a functor. So if I take the identity map, I get back the identity map. That actually follows from the inverting condition, but that's, anyway. there's also the functoriality property, the compositionality of Bayesian inversion, which says if I have two successive stochastic maps and I apply and I get their Bayesian inverses, then the Bayesian inverse of the composite is equal to the composite of the Bayesian inverses in the opposite order, as one would naturally expect that it has to go in the opposite order. And summarizing this using the language of category theory, this says that this category of states is what's called a monoidal inverting dagger category. So this was an observation that I think was made precise by Tobias Fritz. And I can now maybe go back to my question and ask, because I think this inverting property is a feature that at least I'm not so familiar with in the literature on dagger categories. Right? Typically, if you have a dagger on a category, what that means is it's an identity on objects involutive functor. So that's what I've been describing here. And this extra condition of being inverting just means that if I happen to apply my dagger to morphisms that actually have an inverse, then this gives me back the inverse too. So you think of this really as an extension. You think of this retrodiction functor R as sort of an extension of the idea of inverting a process. And I kind of want to really emphasize that this gives you an alternative perspective on what Bayesian inverses are, potentially outside the context of Markov categories. So I should pause again, because at this point, I will talk about extending these ideas to the quantum setting. Any thoughts or comments? Even things like, I have never thought about Bayes' theorem in this way, or we've had several talks in this colloquium on describing Bayes' theorem from string diagrams, and this is quite familiar. I don't know, you know, what intersection the audience has. But please interrupt me if you think you'd like to share a comment or question.
Just on the question about this inverting word, Arthur, I guess it says that in dagger category terminology that every isomorphism is unitary, right?
So I think, from what I remember, I think there was a subtle distinction between unitary. I had once remembered what the subtle distinction was, and now I forget. I think
Not just an isomorphism. Dagger is the inverse.
Yeah, I think this is stronger than unitary. This is saying that the dagger equals the inverse. And I think, correct me if I'm wrong, I think unitary meant that the dagger is invertible, something like this.
No, I think it's the dagger is the inverse. Maybe somebody else can back up or contradict. At least in the terminology I'm familiar with.
Okay.
But yeah, maybe there's something I'm not remembering.
Okay, well, yeah, or maybe also it's been a while since I thought about if there was a distinction between unitary. But in any, so if that's the case, then if this is the definition of unitary, then unitary is probably the better word to use here. Actually, now that I think about it, I don't know if I like unitary so much.
Well, it's interesting motivation for why the Bayesian inversion is not going to work so well in quantum settings, maybe. Or probably not everything's going to be unitary. Anyway.
Right. No, I guess I just mean unitary means something in quantum mechanics. And for me to call this retrodiction functor unitary might confuse people because its input can be a unitary operator. But it's right, the image will be the adjoint. I don't know. It sounds a little strange for me to call something unitary when I apply it in the context of quantum theory. But anyway.
Excuse me, I suppose you give examples where F inverse doesn't exist, and so dagger is not equal to
Thank
the
you.
inverse.
Excellent. Actually, this is an excellent point. I didn't create a slide for this, But let's go back to the category the category finstock, where the objects are finite sets and the morphisms are stochastic matrices. I could ask, if I wanted to, if there exists such a functor there, right? It's an identity on objects, inverting involutive monoidal functor. I'm fairly sure that no such functor exists. And my reason for that is, first of all, the only time you can have a stochastic map that's actually invertible is when it is a bijection. So when it corresponds to a permutation, that's one fact. I could try, so at the very least, I have such a functor R defined on the subcategory of bijections. If I tried to enlarge that category, I could try to do it, for instance, in the following way. I can take what are called bistochastic matrices. So these are matrices that, when I write them down as a matrix, not only do the sums of the entries in a given column add up to 1, but the sums of the entries in a given row also add up to 1. This can be interpreted as saying that it takes the uniform probability distribution to a uniform probability distribution. That subcategory also has a notion of this retrodiction that satisfies all of these properties. However, I'm fairly sure that one cannot go beyond that subcategory. One cannot extend that definition, which in this case, by the way, is the transpose of the matrix. The transpose of the matrix gives you this retrodiction. But I don't think that functor extends beyond that subcategory, meaning there does not actually exist such a functor. And my reason for using the category of states is because by keeping track of this extra information, I am able to extend this functor to now all stochastic processes. So I don't know if that answered your question, but that's also part of my motivation for why I'm working with this category and not just the category finstock, because I don't think finstock has such a functor on it. I don't know of a reference that rigorously proves it does not, but I believe that's the case. Somebody had raised their hand for a question. I don't know if they want to still ask more. Yeah.
Maybe it's me. So we have a question here. Do these properties here characterize Bayesian inversion?
Great question. Great. I mean, in some sense, I'm leading you to ask these questions.
Awesome.
Yeah.
Thank you.
So it is, there are some claims that these axioms do characterize Bayesian inversion. There was a talk at the New York Category Theory Seminar that claims to have a proof that they do. I haven't fully gone over the proof yet myself, but I believe that it may be true. Part of my motivation for describing these axioms is my hope that it is true. But excellent question. Any others? Okay, great. So now let's move on to the extending these ideas to the quantum setting. So I'm not expecting you to be an expert in quantum mechanics or anything like that. I'm just going to try to throw out some definitions. If it's the first time you're seeing them, hopefully the other aspects of the talk that I'll be mentioning are more approachable. So quantum states in this case are modeled by positive unit trace elements of finite dimensional C-star algebras, at least quantum states for typical finite dimensional quantum systems. As an example, the algebra that's often of interest is the bounded operators on a Hilbert space. And again, since I'm doing finite dimensional things, this is a finite dimensional Hilbert space. Pure states are kind of like the analogs of having Dirac delta distributions. They are rank 1 orthogonal projections in your Hilbert space. Mixed states are self-adjoint operators with a discrete spectrum that forms a probability distribution. So non-negative elements that sum to 1. That's what a mixed state is, also called a density matrix. And here's just a rough picture about what happens, the distinction, maybe perhaps understanding a slight distinction between the setting of classical probability of 2 elements, where you have 2 elements, then the set of all probability distributions on those 2 elements forms a 1 simplex, which I've drawn here on the left for bit. And there's also a qubit, which corresponds to the set of states on the Hilbert space of 2-dimensional complex vectors. In that case, the set of pure states is diffeomorphic to a sphere called the Bloch sphere. And the convex hull, all convex combinations of those pure states form the set of all mixed states. So the interior of this sphere, the Bloch ball. So there's a, sort of a big distinction between the 2 convex spaces. And so, as I mentioned, in the finite dimensional case, the algebra is just m by m matrices. So really, if all of this sounded really complicated to you, just think of Hilbert space and its associated algebra as matrices, square matrices. And mixed states, so density matrices are matrices whose eigenvalues are positive, and they are self-adjoint.
Oh,
could you
quickly, if contrast this with the notion of a quantum state being an element of the Hilbert space?
Great question. So typically, when you first learn quantum mechanics, you are exposed to the idea that, like the wave function is a state in your a state in quantum mechanics, and you typically write it as a normalized element of some Hilbert space, usually written in like notation psi or ket psi. I'm also interested in thinking about ensembles of pure states. So like Alice can, for instance, prepare a pure state psi with some probability, and also another pure state psi with another probability. And the mathematical object that describes the probabilistic preparation of these vectors in the Hilbert space mathematically corresponds to a self-adjoint operator with discrete spectrum forming a probability distribution. And in fact, this is really the key object that describes the statistics of the state that you're describing. So the one you're thinking of is a special case where I take the projection operator associated with that single vector you're thinking of, I think, if I interpreted your question correctly. Does that help?
Yes, thank you. Thank you.
Perfect.
Could I also ask a question?
Yep.
At the top right corner, you have finite dimensional.
Yes.
Immediately, well, 2 lines below you have separable, which seems to be
Yeah,
automatic.
you notice
I'm not misinterpreting anything here.
No, I wrote it in green, and then I realized, oh, I forgot to erase because I
got to erase it in green.
Yeah, I should have erased the separable just because it's automatic. Yeah. Right. So okay. So evolutions. I'm gonna skip this definition because it's a little bit technical, but the idea, so I'll leave this up while I say what I mean. So the evolutions are described by quantum extensions of what stochastic matrices do. And stochastic matrices take states to states. Evolutions in quantum mechanics do that plus a little bit more. They take states to states, but they also are closed under the tensor product. When you look at the set of all those possible maps, you arrive at what are called completely positive trace preserving maps. So from the categorical perspective, it's just like a tensor closure of something that's quite physical, namely I take states to states in a linear fashion. And the technical definition is here if you wanted to read that. But you don't need to know that technical definition to understand I'm just mapping states to states with these evolutions. So with that's just that bare bones background, we can try to define an analog of Finstock. And the objects here are finite dimensional C-star algebras. Morphisms are these evolutions, these quantum channels. Composition is the function composition of linear maps. And the tensor product is the monoidal product, is the monoidal structure on this category. The complex numbers is the monoidal unit. And that means that states are given by, in this case, you can think of this as giving you an element of that algebra A. Why? Because it's linear, so it's determined by the value of the number 1. The number 1, if I compute its trace, well, that's 1. So the image, because it has to be trace preserving, means the trace of that element in A has to also be 1. So it's a matrix with trace 1. And also, because alpha is positive, that matrix has to be positive. So this gives me really the thing that I talked about before, which was a density matrix, if A is a matrix algebra. So these really do describe the states in this setting. And the complex numbers is still terminal just by taking the trace. The trace on your algebra, the trace of matrices, for instance, defines for you the unique map to the complex numbers on any algebra, on any finite dimensional C-star algebra. However, given all this structure, it's not a Markov category, and the reason is because there's no copy map, and sometimes that's colloquially called the no cloning theorem. But I can still try to look at its associated category of states. By the same construction I had before, I can still look at this co-slice category. The objects are pairs of an algebra together with a state, and a morphism is a quantum channel that takes the initial state to the final state. So what is this structure that we have here? In this case, we have what's called a semi-cartesian category, and this definition looks almost exactly the same like the one of a Markov category, except that this is a sentence with a period at the end of it, and it's a symmetric monoidal category where the monoidal unit is terminal, period. So there's no requirement of having a copy map. And although the quantum Finstock is semi-Cartesian, it's not a Markov category, we can still ask, can we define Bayesian inversion here? And there are two attempts that one can try to do this that I'm aware of, and historically speaking, this is the way that I was thinking about this. This one I'll sort of kind of skip just due to time, but the idea is that we try to use what are called quantum Markov categories. And the idea here is to still define this copy map I had mentioned earlier. There's a technical way to define it. It's basically coming from the multiplication of two elements in your algebra. And it's not a positive map, but we can still try to define Bayesian inversion using the string diagrams. The only thing is that these string diagrams no longer live in the category of physical processes because neither of them is a physical process. You think of this as a mathematical extension, but you ask for this map, E dagger, in the opposite direction to nevertheless be a physical process. So there are a bunch of problems with this attempt. The first one is that this is rarely a physical channel. It doesn't take states to states. And I perceive that to be a big problem because if I want to do inference, I want to make sure that I'm preserving probabilities. You can also ask, well, why not use a different kind of copy map? Why not do the multiplication in the opposite order? Or why not take the Jordan product of two, which means combining the two multiplications and then weighing them equally. That leads you down a whole rabbit hole of what are called quantum states over time, which is like another direction, somewhat orthogonal to this one. But the point is that understanding this is quite subtle. Finding out other ways to do this is a little bit subtle.
Arthur, you're at 50, so you're starting to eat into question time, although you've had plenty of questions.
Got it. Okay, good. Thank you. Hopefully it's wrapping up. So instead I'll focus on the semi-Cartesian perspective. And that's the perspective of using the dagger retrodiction functors I had mentioned earlier. So the idea is very simple in this case. It says you take a semi-Cartesian category, construct its category of states, you define what's called a retrodiction functor on this category of states as an identity on objects, inverting, involutive monodal functor. All those properties that I had mentioned earlier. And you say that the application of this functor on a given morphism is called the Bayesian inverse of that morphism. That's you define a Bayesian inverse in this way. And the theorem is that a retrodiction functor on the category of quantum states exists. There's a formula for it. I won't talk about it. And I'll just say that it reproduces the usual one of classical Bayesian inversion when you restrict to commutative algebras. And the interesting thing is that this inverse map, this what's called the Petz recovery map, doesn't satisfy those string diagram conditions I wrote before, but it nevertheless is still a retrodiction functor. And in fact, the functoriality properties have been used in the literature for error correction purposes and understanding bounds on data processing inequalities. So it actually gives you a lot of useful information in the context of quantum information theory. I find this quite surprising. I don't know what your thoughts are on that, but I found it quite surprising that quantum information theorists were using functoriality specifically to describe the usefulness in such a setting. Okay, this is like a one-slide summary of what we did. We looked at Markov categories, and they provided a robust framework of Bayesian inversion for classical probability theory using string diagrams. But unfortunately, the definition is limited when transferred to quantum systems and their evolutions. And instead, we focused on the key properties of the assignment sending a map to its Bayesian inverse. And we defined retrodiction functors in Bayesian inversion using those ideas in terms of the co-slice category. And we can therefore extend Bayesian inversion in a robust manner that includes both classical and quantum systems using semi-Cartesian categories. There are tons of open questions that I don't know the answers to. One of them was I already alluded to earlier. You can ask the same question for this category of quantum states. You can also ask more abstractly, which would presumably answer the first two questions. What structure properties on a semi-Cartesian category guarantee the existence and uniqueness of such a retrodiction functor? And then once you have this in mind, what examples are there outside of classical and quantum probability that allows you to provide a fruitful way to invert morphisms in your category? And what can you actually do with that? So with that, I thank you. I thank the audience. I thank my collaborators. Primarily for this talk was Francesco Buscemi, but also James Fullwood, Luca Giorgetti, Alessio Ranallo, and Benjamin Russo, and my funding agencies. And here's a rough picture that summarizes what this retrodiction map does on certain subcategories of evolutions. Thank you.
Great, thank you, Arthur. So we have time for questions, about 5 minutes or so. Does anyone, if you have a question, you can either raise your hand and I'll call on you, or Arthur will, or you can just unmute. So Kevin?
Sure, thanks again, Arthur. That's pretty cool stuff. What are reversible channels? Just trying to understand your little cartoon.
Oh, good. So in that case, reversible here just means by isomorphisms.
So those, it doesn't feel obvious why these are like some subclass by stochastic things, but I guess I might have to write down what these actual objects are.
Yes, okay, good. So let's take permutations. The inverse of a permutation is its transpose, right? That's one fact. Second fact, if I have a bistochastic channel, then the transpose of that matrix is also a stochastic matrix. And so permutations are a subset of that. So and then you can also think of this in the quantum setting as well, which has its own generalizations too.
Yeah, I think the non-classical reversible channels are what I can't get in midair, but that's fine.
I see.
Yeah, thanks.
They're called unital quantum channels, and a special case of those is unitary quantum channels.
Right, which also probably explains why you don't want to use this word unitary for the
Yes.
dagger, because
Yeah.
there's two daggers.
Yeah, exactly.
Yeah,
Exactly. I
yeah,
don't want to
yeah,
conflate. I don't want to conflate those two usages of the word unitary. That's correct.
yeah, that would be scary. Right, agreed. Okay, yeah, thank you.
Thank you for the question.
Great. Are there other questions?
I have a question.
Yeah, I have
Go ahead, Xiaowei, you were first.
Oh, okay. Yeah, can you talk more about the pets? What functor? So if you have a pets recovery map, if you have a quantum channel, what does it mean to reverse that? So are you saying that if I observe a certain quantum phenomenon, I can make some predictions about what happened before?
Yes, so you can make predictions. They are not fully accurate. The PETS recovery map is what's known as an approximate recovery channel. So there are certain inequality bounds between the fidelity of the actual states that gave rise to that outcome that you see, and it wouldn't give you the exact state you started with. That if you knew that, that would be a perfect error correction. But in general, perfect error correction doesn't exist. When perfect error correction does exist, the PETS recovery map does give you the perfect error correction protocol. But when perfect error correction does not exist, the PETS recovery map gives you an approximate recovering procedure.
Okay, thank you.
Great,
Yep.
thank you.
Thank
And
you.
very quickly, Seth, did you still have a question?
this is a wild cross subject question. Can anyone think of a connection with matrices whose row sums and column sums are all one, but have signs or plus or minus 1, 0 entries in which the signs of non-zero elements alternate across each row and each column? In other words, I guess is there any sense, say even a little bit more general, where instead of the rows and the columns is stochastic, where the column sums, but the entries may be complex or have sign or be signed?
Yeah, that's an interesting question. So I think I only have a comment because I never looked into the literature for this, but I have heard somewhere that Dirac had at one point in his life studied such what are called quasi-probabilities. And somebody claimed to me that Dirac also had a Bayes rule in this setting of quasi-probabilities. So I believe that your question has an answer. I don't know what it is, but if you look up Dirac-Kirkwood probabilities, I suspect you might find the answer to your question.
There's a little glitch. Arthur, you said Dirac and then what probabilities?
Oh, Kirkwood, Kirkwood.
Great.
I suspect that you might find the answer to your question. Probably looking up Dirac's original paper on the subject.
Great. Thank you very much. And thanks for the question, Seth. I think let's thank Arthur again and turn off the live stream. And then if people have more questions, they can ask maybe now.
Oh, right. I forgot that. Yeah, I was worried. I was concerned that that was the strict cutoff. Yeah, I'm happy to